Good morning. In 2021, at this ISPD, I showed you how IBM was planning to double quantum volume each year. I'm happy to report that since then we have made progress on schedule and announced a 512 quantum volume system last year. The improvements have largely come from improving the physical error rates of the individual qubits. If you look at the systems that we have online that we post on our website, you kind of can see that the error rates of 4 times 10 to the minus 3, for example, for this device, and we're starting to see coherence times of several hundred microseconds. On our best devices, our qubits are 99.9% reliable, and we are getting to 1 millisecond coherence times, allowing for longer computations. But we also realized that in addition to the quality of the qubits, scale and speed are equally important to run important applications. Scale is measured in the number of qubits in your quantum system, and speed is measured by the CLOPS, circuit layer operations per second. To improve the scale, we released our 433 qubit Osprey chip in 2022. This chip uses multiple layers for the qubits itself, the readout circuitry, and the wiring to connect the qubits together. The initial results for such a large chip look very respectable with good coherence times. But as you can see from the connectivity map, mapping logic circuits to such complex physical devices start to be pretty interesting EDA problems. Given the number of qubits, the limited connectivity, the varying reliability of the connections and the qubits itself, and you still need to fit the computation within the coherence time of the entire chip. I will not go in too many details, but Robert, in the last presentation in this session, will talk more about the kind of mapping and optimization problems here. In addition to looking at single chip devices, we are also looking to connect multiple quantum chips together. Here you see an example of our Heron chips, where we're doing this using classical communications. Of course, that means we need to map from the quantum domain to the classical domain. Interesting enough, a technique exists that uses circuit knitting, which uses quasi-probability simulation that allows us to implement these gates that straddle between the chips. Unfortunately, this comes with very significant overhead, so we need to minimize the number of gates that actually straddle the chips. And for each of these gates, we need to make sure that they only use a very localized communication with very localized signals, to minimize basically the simulation that needs to take place there. Again, interesting partitioning problem to map the logic circuits to the physical circuits. In addition to the classical communication, we're also looking to enable quantum communication between the chips. Likely these connections will not be as reliable as the coupling of the qubits on the chip itself. However, this can still be a step up from the overhead that comes with the circuit knitting that I described on the previous page here. And finally, we are looking at quantum communication links to actually connect modules in different refrigerators together and build one large quantum system out of these. So you see very different partitioning techniques that each leads to very different problems in mapping your circuits. But hey, partitioning of kind of nasty circuits with nasty constraints is something that this ISPD community has done for a long time. So we're counting some key innovations from this community to also improve the mapping in our quantum systems. So by putting all these techniques together, we hope to scale to 400 plus qubit systems in the next couple of years. But in addition, we also realize we need to work on speed. Yeah? And speed is mostly determined by kind of seamless synchronization of the quantum circuits with the classical circuits through the control circuitry. So one big piece of the control circuitry is basically the wires that go from the qubits to the digital communications. With these large number of qubits, we cannot accommodate individual wires anymore. So we invented these flex cables that also allow that even work in these cold temperatures, but allow us for a significantly larger number of wires to communicate. In addition, we have also significantly advanced the control circuitry, so that they not only can control the larger number of qubits, but also allow for dynamic circuit processing. This allows us to do mid-circuit measurements in the middle of a quantum computation and make decisions based on these measurements. Think about it as a big if-then-else statement in the middle of your coherence time of your quantum computation. This has allowed us to significantly speed up 10x some key circuits and break the 10 k-clops boundary that we set for ourselves to break last year. But even more important, these dynamic circuits are essential to allow error correction to take place. They allow us to do syndrome measurements across multiple physical qubits to detect the presence of errors and correct for them. As you can see, we are marching along, and with us a large number of users who routinely run more than 3 billion circuits a day on our systems and have produced over 1,700 papers using IBM's quantum systems. We see more and more opportunities in quantum simulation and machine learning in the near term, and linear algebra and other optimizations in the longer term. We hope you use all these resources to jump on board with us. Thank you.